Okay, chapter 6. We are talking still about probability distributions, but in chapter 6, we're going to focus on another type of distribution. It's the normal probability distribution. Okay, and one of the key things that I want you to note as a difference between the normal distribution and the binomial distribution is that the normal distribution is for a continuous random variable, and the binomial was for what? Fixed, or we called it what? Discrete. Remember, discrete versus continuous? Okay, so now we've got some different situations, but we also have some similarities between the two. Okay. Near the end, the very last section, I think, in this chapter will bring together how we can use the normal distribution to approximate the binomial, and we'll even talk about why. But anyway, I put up here the formula that gives us a normal curve. If you were to put this into your calculator with some numbers in for mu and sigma, then you would get a curve similar to what we see here. Okay. The normal distribution, in short, though, is a symmetric bell-shaped distribution, and it's described by the formula that we have here. There are many different normal distributions. However, what makes one different from another is simply the mean and the standard deviation. Everything else in this formula is a constant. The standard deviation, we would determine pi is a number, right? Approximately 3.14. E is a number, approximately 2.718. But the only thing that's not known is the standard deviation and the mean, and then of course the various x values that we might plug in. All of them would have shapes similar to these shapes that we see here. Both of these are normal distributions, except this first one has a mean that's smaller or less than the mean of the second. Can you see that? Because the mean is a measure of the what? Center. Okay, so we could lay these on top of one another. They look the same, except the center for this one is over here versus for this one's here. These two have the same center. They have different what? Or, I guess we could say ranges or standard deviation, different spread, right? But still, they're both normal distributions. So since we have so many different normal distributions, we usually talk about the standard normal distribution. Okay, it is a normal distribution categorized let's say with mean equals 0 and standard deviation equals 1. Okay, when we talk about the standard normal distribution, we're talking about a normal distribution that has a mean of 0 and a standard deviation of 1. And you might think, well, how often do you incur that? Well, probably not a lot in a natural setting, but we're going to talk about how we can transform any distribution, any normal distribution, to be a standard normal distribution. We'll talk about that later. As far as requirements for the standard normal distribution, the correlation between area and probability. Okay, and this does go with the requirements for the standard normal distribution. When we looked at requirements for a probability distribution before with the discrete, there were two requirements for it to be valid. What were they? Okay, all the probabilities have to be between 0 and 1, and They have to add up to 1. Okay? We still have the same thing here. All the probabilities will be between 0 and 1, but the area beneath this entire curve will be equal to 1. And so everything that falls beneath the curve, is part of the probability. That's all that can happen. So that entire area equals 1, which makes it nice because all the probability should equal 1. So there's a direct correlation between area and probability. If you know anything about calculus, one of the things we do in calculus is we can use integration to figure out the area beneath the curve. And in an advanced calculus class, you could take the formula that we had above, integrate it, and you would find that the area beneath this curve has to be equal to 1. But anyway, for us, what we need to know is that the entire area beneath the curve, the normal distribution curve, is equal to 1. And that helps us to relate it to probability. All right, so how do we find these probabilities? There'll be two things that we'll use. We're going to use our calculator, and we're also going to use a normal distribution table. Okay, and that's what we're going to focus on for the rest of this first little section, is how to use the table, how to use the calculator. Okay. All right, let's see if I can find that table. The funny thing about these tables is they're copyrighted. However, they really do result just from, that formula. So you would think you couldn't copyright something like that, but apparently you can. Let's see if I can find it. However, usually, it's almost copyrighted by the publisher. And we're usually using the same publisher. So this one actually came from a different textbook, but it's close enough. It looks awful, though. Okay, can you all kind of see this? Kind of, sort of? Okay. This is available in your text. I think it's in Appendix A in the textbook that we're using. And what else did I want to tell you about it? Yeah, so I will provide copies of this table for the test. Okay, but again, I'm going to show you how to do this on the calculator as well. Whenever you're looking at anybody's normal distribution table, you really need to pay attention to this picture first, because this picture describes or lets us know what these numbers describe for us. Okay, we're going to be looking at z-values for data, and here it tells us that the area described is for the area to the left of this z. Does that make sense? Okay, that's what you need to keep in mind. Some textbooks will have area to the right. I was helping a friend the other day. Her textbook had an awful situation. I felt really bad for her. It was different columns depending on whatever you were looking at, but for our textbook, it's going to be the area to the left of z, okay? Which allows us to figure some things out. What if I wanted the area to the right of z? What would I do? Subtract it from 1. Whatever area I found for this particular z value, we could just subtract that from 1 to figure out what's left over here, okay? Now, let's take a little look at the table. The table has two parts. On the leftmost column, this is our z-value out to the first decimal place. And then if we go across the column to, go across the top to the right column, we can get that second decimal place. So these are all z-values. The leftmost column and the top make up z-values for us. What we see here in the middle is going to be our area or our probability. Okay? All right? So that's going to be important. Make sure when you get your table in your hand, if you're going to use that, you make a note or a distinction between z-values and areas, because sometimes we'll be given basically a z-value, and ask to find the probability or the area. Sometimes we might be given an area, and then we need to go out to the top and sides and find the z-value. Okay, so how does this work? The first example on your handout there asks us to find the probability that z is less than negative 1.82. All right, so what I would do, I'll do it here. What I would do first of all is kind of make a picture. Okay, if we're talking about z's, first of all, right here in the middle, z is going to be equal to what? Not 1, 0. Okay, remember the standard normal distribution has a mean of 0. That's going to be at the center, and a standard deviation of 1. Okay, to the left of z equals 0, we would have negative values. Okay, so I might put minus 1.82 out here. And then I'm interested in the area that's less than z equals minus 1.82, which is going to match up exactly with what the table would give me. Does that make sense? So I would go to my table, if I can get to it quickly. I'm going to go down to minus 1.82. Okay, here's minus 1.8. I'm going to go until I'm beneath the heading for 0.02. See, that's 0.02 right there. You see that? Okay. And so it tells me that the area to the left is 0.0344. And that's my probability. Okay. Equals 0.0344. Is that what I said? Okay, good. Not so bad, right? Okay, the table is broken up into two halves. So the half that we were looking at just now, that had negative z values. But now if we go on beyond z equals 0, then we're going to get positive z values, and all of the areas would have to be at least how much? Not at least 1, but at least, what is it? 0.5. Is that what I heard? Right? Because this is halfway. So once I get beyond this, remember our table tells us the area to the left of z. Okay? So let me find the other table. This was the negative table. Let's see if I can find the positive one. Okay, this one is the positive one. Okay, so notice all the values, if you can see that, are greater than 0.5 in our areas. You see that? Okay, yes, no, maybe? Okay. All right, so what number are we looking for? Z? What was it? Was it greater than or less than? Less than 0.38. So I'm going to come down to 0.3, and I'm going to go until I'm beneath 0.08, and so I've got 0.6480. Okay, equals 0.6480. Okay, if we've drawn a picture, we would have 0.38 over here somewhere, and we know when we look up that value in the table, it describes all of this area, which is the area that we wanted. Okay? All right, what happens if we look at the probability that z was greater than 1.82? Okay, what would we get? Okay, again, I would draw my picture. Here's my 1.82. I want to be greater than that. So there are two ways we could get the answer. First, let's assume we didn't know anything else. What would I do? If I look up 1.82 in table 2, I'm going to come down to 1.8. Okay, 1.8. We're going to go beneath that 0.02 heading. I see 0.9656. Okay, that describes which portion of my chart. This portion or this portion? Okay, the left portion. What was the number? I forgot it already. 0.9656. Okay, so if I want to know the probability of being greater than that, we already said we're just going to do what? Subtract that from 1. 1 minus 0.9656. What does that come up to? Okay, 0.0344, which is the same thing that we got when we looked at what? Being less than negative 1.82. Why are they the same? Okay, how do we know it's the same area? What is it about the normal distribution curve that makes those the same? It is what? It's symmetric. Okay, so if we'd done this one and we noticed, oh, well, that's just the flip side of what they're asking us for now, we could have said, oh, by symmetry, it's 0.0344. Okay, if we had done this one before. If not, then I would do it just the way that I did it. Okay, well then, with that said, I think the next one was for probability that z is greater than 0.38. All right, what are we going to do with that? Okay, 1 minus. So it's going to be 1 minus 0.6480. We looked up 0.38 earlier, but this time we're interested in being greater than. Okay, and so we're going to say the table value is what we get right here. All right, we're going to do 1 minus that table value, and that comes up to what? Okay, 0.352. Questions about that? All righty. The authors suggest, and I agree, that for the types of examples that we looked at just now, using the table is probably easiest. Okay, although I will show you how you can do that on your calculator in a minute or two. For this next type of example, especially this one right here, using the calculator may save you some time. But we'll do it by the table first, then I'll show you how to do it on the calculator. Okay, so on the table, I've got to draw a good picture, really good picture. Okay, here's 0. 1.78 might be right here. 2.33 might be right here. Okay, and basically I want the area between these two. All right, using the table, and keeping in mind that when we look up these particular values, it describes the area to the left. What might I do to figure out the area between the two? What's that? Okay, all right, look up 2.33, right, which would describe all three of these pieces, right? But then subtract from that what I get when I look up 1.78, because I don't want these two. And these are what's left over when I look up 1.78. Does that make sense? Okay, so
What you're saying is you would look up the value for everything left of 2.33 and then subtract everything left of 1.78.
78. That's right.
That's
8.
the space between the two of them?
Yes. Look up the value for what's left of 2.33 and subtract from that the area that's left of 1.78. So when I look at my table, for 2.33, I get 0.9901. Remember that. And for 1.78, I get 0.9625. Okay. All right, I remembered the 0.9625. 0.9901. Okay, we're going to subtract those two. And so we get what?
0.0276.
Okay, 0.0276. Okay, questions about that? All right. The next one is pretty much the same, except I really don't have to look up two values because I already know the area to the left of 0 should be what? 0.5, just 1/2. So the only thing I really need to look up is 3.08. I don't want all of it to the left. I just want what's between it and 0. So for the area that I find, I'm going to subtract 0.5. Okay? So if we look at 3.08, okay, 3.0, let's see, 0, 1, 2, 3, 4, 5, 6, 7, 8. I got 0.990. Okay, and so we're going to subtract from that 0.5, so we get 0.490. I may have left out a 9. What was it? 3.08? 0.9990. Okay. Okay, good. Questions about that? 4990. Yep. Okay, we know automatically for 0 the area to the left is 0.5. Again, because of symmetry. And also the area to the right would be 0.5 if ever we needed to know that. Okay? That's the table. How do you feel about the table? It's okay. It's not the worst thing in the world. Now, let's take a look at how we would do this on our area and probability. Yes. Okay. We're going to go back, though, and look at some of those and how we would do them on the calculator. So let's do the one where we were looking at the probability of 1.78 being less than z, less than 2.33. Okay. We're going to use what's called normal CDF. And the syntax for that, let me write that real quickly. Is lower bound, upper bound. And the default values for the mean and standard deviation are 0 and 1. Okay, so we can just, if we don't say anything, it'll assume 0 and 1, which that's what we should do all the time. Okay, so looking at, we were looking at 1.78 to, what was the other number? 2.33. Okay, then if I'm interested in this area, the lower bound is 1.78 and the upper bound is 2.33. So that's what I'm going to put in on my calculator. All right, so here it is. Remember we went to the distribution menu last time? This is under that same menu. So I'm going to go to second, the distribution key or the vars key. Okay, and number 2 is normal CDF. We'll use number 2 every time. All right, when we're trying to find a probability. So number 2, my lower bound we said was 1.78. Upper bound is 2.33. And 0.0276. Is that what we got when we did it by hand? Using the table? Yes. Okay. So that was easy, right? We didn't have to look up all the and stuff like that. What makes it a little difficult is, and it's not that difficult, is when our upper or lower bound is plus or minus infinity. Okay. So, for instance, let's say I wanted to look at, I think we had the probability of z being greater than 0.38. Okay, when I draw that picture, okay, my lower bound is 0.38, my upper bound is infinity, because this curve keeps going on and on and on and on and on and on forever. Okay, so the upper bound is infinity. Well, we don't have a symbol for infinity. You can't plug in infinity. But what we can do is just put in a really big number. Okay, so it's still not that bad. If I wanted to do this, I'd say my lower bound is 0.38 and my upper bound is like 10,000. Remember, this is a normal distribution curve. And think back to the empirical rule. Remember the empirical rule? Within 3 standard deviations of the mean, how much of our data did we have? 7. 99.7%, almost all of it. So if I say that z is 10,000, it's not going to add any more than 0.3%. That's all that's left over, right, outside of 3 standard deviations. Does that make sense? So just put in a big number. It'll be okay. All right, so we're going to go from a lower bound. So I'll do second distribution, normal CDF. My lower bound was 0.38, comma. My upper bound is big number. Close parenthesis. And we get 0.352, which I think that's what we got when we did it on the table. Okay? So sometimes that bothers people, that putting in the big number, and some textbooks tell you to use the scientific notation key to make it really big. That's not necessary. Okay? Just put in a big number, and that's what we'll pretend to be is infinity. Or if we were going from lower bound, we'd do negative big number. Okay? All right, questions about that? Now that's just kind of like a tool. Okay, that's not the main point of this chapter. But you got to be able to either use the calculator or the table or both so that you can get everything else that we're going to talk about. All right? Now, one more concept about the table before we go to some applications. Where's my paper? Hi, yes. Okay. What we just did, I like to summarize by saying we had a z value, and we used that to find an area or a probability. Okay, and in a minute, we're going to take some x value, convert it to a z value, and then find area probability. Okay, in these next set of problems, we're going to turn that around. Most of you are too young to know about Captain Kangaroo. Anybody know Captain Kangaroo? You do. Captain Kangaroo was a great show back in the 70s, 60s, I guess. And he had this little segment about Mr. Green Jeans. Do you know Mr. Green Jeans? Sounds familiar. Okay, well, Mr. Green Jeans wore green jeans. He had a green jean jacket. He had green jean pants. All right, kind of like Brent's jacket back there. But anyway, with Mr. Green Jeans, you know, this technology was not at all what it is today. So Mr. Green Jeans would go into his little cottage. He would go to the refrigerator, get some milk. He'd go to the cupboard, get a glass. He'd pour the milk into the glass. Well, the fascinating part of this was when they rewound the tape, right? The milk would come out of the glass, back into the carton. He'd back up to the little cabinet, back up to the refrigerator, and he'd back down to the door. They just turned it around. We didn't have much, okay? That was entertainment when I was a child. So I mentioned that here because that's what we're going to do. We're going to turn this around. Here you see it says finding z-scores given the area. So I'm going to look at the area or probability, okay, and then we're going to go on that table to find a z-score, and eventually, once we get to our applications, we'll be able to convert that z-score back to an x value. And we can do that via the table or the calculator. And of course, I'll show you both. Yes, z-score, z-value, same thing. Okay? All right, so here, they're not asking us, oh, let me mention this as well. The expression z alpha over 2, and let me take the 2 off for now. We'll save that for another day. Okay? The expression z alpha denotes the z-score with an area of alpha to its left. Okay? Scratch out right, put left. Okay? It's the z-value with an area of alpha to its left. So in this example, when it says find the value of z 0.25, okay? Yeah, just scratch off the 2. Right. Okay. We'll talk about alpha over 2 another day. But I'm going to put a line along this curve such that I've got about 0.25 to the left. Right? Should that line be on the left side or should it be on the right? The right? Okay. Well, actually it's going to be on the left. Okay, because remember, our table describes area to the left, and remember, we're kind of starting from over here where area would be 0, and then we keep increasing. When we get about halfway, area is 0.5. When we get all the way to the other side, area is 1. Okay, so for values less than 0.5, we would put that line to the left of the center. For values more than 0.5, we would put it to the right. But I've got an area of 0.25. Not a z-value, an area. Okay, and I like to circle it to remind me that it's an area, not a z-value. Okay, does that make sense? If it was a z-value, we would have put it on the right, but it's not, it's an area. Okay, so I want to find the z-value that describes this scenario. So what I'm going to do is go to my table. Since it's 0.25, I'm going to go to the first half of the table. And I'm going to scan through my areas, not the z-values, but the areas, until I get as close as possible to 0.25. Where's my table? Yeah. Okay, so if I scroll, .21, 27, let's see, where's my 25? Why can't I find it? There's 0.240 and 0.23. Okay, what's the next one? 24, 24, 2514. I would go with this one because it's a little bit closer. The z-value that goes with that is, if we go all the way out to the edge, negative 0.6. And if we go over to the top, I can't see it, but it'd be 0, 1, 2, 3, 4, 5, 6, 7. So we'd say negative 0.67. Okay, negative 0.67. Negative 0.67. Okay, z 0.25 is equal to negative 0.67. Okay, questions about that? All right, let's do one more before we look at calculator. Okay, find the value of z 0.78. So this time we're going to be left or right of center. Right, okay. And so we make a mark such that the area over here is 0.78. And we want to figure out which z value divides the data like that. Okay. And so I would get as close as possible. I'm going to use the second half of my table. I'm going to get as close as possible to 0.78. There's 0.7794. That's pretty close. It's farther away. So when it comes to, you know, which one to go with, I'd go with the closer one. There are a couple of values that have kind of special things, and we'll split it right in the middle. But otherwise, we just go with the one that's closest. So 0.7794, that corresponds to a z-value of 0.7, and this should be what? 7.77? Yes? Okay, 0.77. We'll take that. All right, 0.77. Questions about that?
Okay, just choose the smaller one.
This is the one that's closer. Closer to the value that I'm looking for. So we were looking for 0.78. 0.7794 is only 0.0006 units from the number I'm trying to target. This was a little bit more. It was 0.0023. So I chose the z-value that correspond to the area that was closer. Okay. Alrighty. The next example is for an area such that it says find the z-score such that the area to the right of z is 0.35. Okay, so that looks like z, I'm going to put it over here because we want the area to the right to be 0.35. Well, what do you think I'm going to do so that I can use my table? Should we look for 0.35? Subtract it from 1, because the table and the calculator will do this as well. They both look at area to the left of z. So I'm not going to look up 0.35. I'm going to look up 0.65 for area. That's an area. This was an area. Okay, so we get as close as possible to 0.65, which is going to be on the second half. Okay, so I've got 0.654. What was over here? That looks like 0.6517. I think that was a little bit closer. Okay, so that value would be 0.3. And I'm not even sure we can see this on the video. All right, do you agree this is the closer one, 0.6517? Yes, I'm going to say so. Yeah. All right, so that goes with 0.39. All right, z equals 0.39. Okay, questions about that? All right. We could talk about percentiles. Okay, remember, let's say we were looking for the 75th percentile. That's not an example that we have here, but then I would draw this so that the z-value has 75% of the data below it, and then, of course, 25% below above. So we would look up an area of 0.75. Does that make sense? Okay. All right, and then this one's a little interesting. They want us to find two z-scores. We want to look at the middle 80%. Okay, I've got 80% right there, which means I have how much left over in the tails? 0.2 altogether, and if the 80% is in the middle, then that 0.2 is going to be evenly distributed. So we have 0.1 over here, okay? That's what I'm going to look up for this first z-value, because the area to the left of it is 0.10. What am I going to look up for this second z-value? 0.9. Very good. Okay, we got to look at the total area to the left. So for this second z-value, we would look up 0.9. Okay, we could write that if we wanted to, as this one is z 0.10 and this one is z 0.9. Okay, And I think you kind of got the table idea. So we'll use our calculator to find those. Okay? For the calculator, we're going to use inverse norm, which you saw there. It was option number 3, INV norm. And the syntax is just area to the left. Okay, we could tell it the standard deviation and the mean, but it assumes 0 and 1 if we don't tell it. Okay, so inverse norm, area to the left. All right, so just to test this to make sure that it works with what we had earlier. Okay, for the first one, we had an area to the left of 0.25. So, for this first one? Yeah. Oh, that's okay. Just kind of testing to make sure that it works. So I'm going to do second distribution. Number 3 is inverse norm. And the area to the left is 0.25. And so we get negative 0.67. Okay? All right, so it works fine. So for this one, if we wanted to do inverse norm, 0.1. Second distribution. Number 3, we'll put in 0.1. Okay, that first value is going to be negative 1.28. Okay, and then our second value, we do inverse norm. .9. Okay, remember that we have to have the total area to the left. So we already saw we had 80% in the middle, plus this additional 1% in the tail. So 0.1 plus 0.8, total area was 0.9. Okay. All right, and we could have guessed that this was symmetric since we put that 80% right in the middle, so it would have been minus 1.28 and positive 1.28. Okay, questions about that? All right. You're going to want to get really good with calculator or table or both. And let me make one more note about calculator to table. All right, so that all of us get the same answers. The calculator, as you see, it'll give us z-scores for lots of decimal places, right? But the table does not. So z-scores, we will round to 2 decimal places. Okay, so if this gives me a z-score, inverse norm gives me a z-score, so I would just call this 1.28 or negative 0.67. All right, even when we get ready to find z-scores again in a minute, we're going to round z-scores to 2 decimal places. Areas and probabilities, we generally round them to 4. All right, that's what the table does, so we'll stop it at 4 on our calculator. All right. Otherwise, you might get some slight differences in your answers.